Dear students, in the previous two lectures we have discussed about the chronic penny model and we have derived the condition for chronic penny model and how the band structures are evolved in this kind of models. Now in this video I am looking at the equation of motion of an electron in an energy band, which is basically given by this expression, and we will derive this expression. Now in the chronic penny model we have assumed electron moving in a periodic potential created by the lattice. Now the motion of the electron we can describe in terms of the wave packet motion. Okay, you know how a wave packet is formed in a crystal. Okay, so the wave packet is formed by the superimposition of several individual waves, each of them having a wave number k, okay, which is very close to each other. Okay, so there are lots of waves, each of them having a wave number which is very close to k value k. Now when we talk about the wave packet, we look at the group velocity of the wave, which is given by d omega by dk, and you also know what is the energy of the wave packet, which is h cross omega. Okay, and using this expression you can substitute for omega, which will give you h cross inverse d epsilon by dk. Okay, now you can also write down this in a slightly different way, which is h cross inverse gradient of k epsilon k. Okay, so this gradient you have to be very careful. This is not the usual gradient, it is the gradient in the momentum space. So you have to define gradient in the momentum space, and epsilon k is the dispersion relation, is the variation of energy with respect to k. Okay, so the group velocity basically depends on the dispersion relation. Now you assume that there is an electric field, and the work done on the electron by the electric field can be calculated using our familiar expression, work done equal to q into v. V is the external potential provided by the electric field. Now we assume we calculate the work done on the electron for a small amount of time delta t. Okay, so the small variation in energy because the work done is stored as energy. Okay, so q is basically minus E, and potential you can write down electric field into displacement, which is given by Vg delta t, the displacement in a very small amount of time delta t. Okay, now this variation in energy you can also write down as d epsilon by dk delta k. So this is the variation in energy due to variation in small amount of k. Now you compare these two expression, and here also you can substitute d epsilon by dk as h cross Vg from this expression. Okay, and you remove this common term, and finally you will get h cross delta k by delta t equal to minus EE, and which is basically h cross dk by dt equal to minus EE, and this is very familiar. This is in the form q times E, which is basically the force acting on the charged particle in an electric field. Okay, so you can write down h cross dk by dt as the force, and this is the what we have done so far is the force acting on the electric field, but this is true in general, basically in the case of a crystal, and this is an important relation. It follows the Newton's law. Okay, and so this force in general contains the force, all the forces provided by the crystal as well as electric field as well as the magnetic field, basically the Lorentz force. Okay, so now we calculate the force acting on the particle electron in a magnetic field. Okay, and we assume here the magnetic field is sufficiently low, otherwise it will lead to Zeeman effect, which you know, Zeeman effect is the splitting of energy levels in a magnetic field. So in that case the band structure of the crystal will be lost. Okay, So we assume the field, magnetic field is sufficiently low, so that the band structure is not broken, okay, it is still there. So, the force acting on the electron you can write down as a Lorentz force. So, the velocity here will be the group velocity of the wave packet and into or cross B is the external field. And for the Vg group velocity, we can substitute this expression h cross inverse gradient of epsilon cross B. Okay. Now, this is equal to you can write down as this is equal to h cross dk by dt. Finally, you can write down dk by dt equal to minus E by h cross square gradient of epsilon k cross B. And you have to be very careful here, because the gradient here, it is everything defined in terms of the momentum space. Okay. So, left hand side you have momentum, right hand side also the gradient is with respect to momentum space only. So, this equation is basically written in the momentum space. Okay. And what does it says? It says that in a magnetic field, the electrons move in k space, okay, in a direction which is normal to which is perpendicular to gradient of epsilon as well as perpendicular to B. Okay. So, it means that you know what is a gradient in the position space. The gradient, the direction of gradient is given by the direction of steepest ascent or steepest rate of change in the function. Okay. So, here also it means the same thing, but in the momentum space. And so, the direction delta k or gradient k epsilon is in the maximum change in the energy in the momentum space. Okay. And the motion of the electron will be perpendicular to this direction. Okay. So, that means the electrons moves in a surface of constant energy. Okay. And in the second case, it means that the electrons moves in a plane perpendicular to the magnetic field. Okay. So, you can take a k value and project it to the in the direction of B, which is kb. Okay. That kb, the projection of k onto B is called kb. Okay. That kb is a constant during the motion. Now, motion in the so the according to the second statement, the motion of the electron will be perpendicular to a plane the motion of the electron is in a plane which is perpendicular to the magnetic field. Okay. And the orbit of the electron is given by the intersection of this plane with a surface of constant energy, because that is given by this first statement. Okay. So, the orbit of the electron is given by the intersection of the plane with the surface of constant energy. So, this is basically gives you the equation of motion of the electron in an energy band. Next, we discuss how the concept of holes are described using the Kronig-Penney model. Okay. The holes, as you know, it is a vacant orbital in a band. Okay. So, you have a energy band structure using the Kronig-Penney model, or electrons moving in a periodic potential, and each of the band, let us say the valence band or in the conduction band, suppose some orbitals are missing. Those missing orbitals or vacant orbitals are called holes. Okay. And these holes will be having certain properties which are described here. You can see 5 properties which is listed in the Kittel book. Okay. So, I will describe one by one. Okay. So, the first feature is that the wave number of the hole is equal and opposite in signature of the wave number of the electron. Okay. So, this is basically arising from the symmetry of the inversion symmetry of the Brillouin zone. Okay. You know, every lattice type has certain symmetry under inversion. Okay. Inversion means R goes to minus R kind of transformation, and similar kind of inversion property will be obeyed by the Brillouin zone of the lattice. Okay. So, this means that if all the bands in the orbitals, if the bands sorry, if all the orbitals in a band are completely filled, then you have a total summation of total wave number will be 0 because of the inversion symmetry. For each wave number we can find an analogous wave number which is opposite in sign. So if you sum over all the wave number, it will be 0. So remember, the summation goes over all the Brillouin zone, all the states in the Brillouin zone. Okay. So so if a band is completely filled, the total sum of the wave number will be 0, and if a particular orbital is absent or vacant, then that is called a hole. Suppose that if an electron is missing in an orbital, suppose you take this valence band. So this is valence band, and the top you have a conduction band, and in the valence band, suppose one electron with the wave number Ke is missing, or this electron absorbs a certain amount of energy from the photon h cross omega, and it moves to the conduction band. So in the valence band there is a electron is missing, and this missing electron is called a hole in the valence band. Okay. So initially when the electron was present in the valence band, the total sum of the wave number will be 0, but if this particular wave number is missing, it is having a wave number of minus k e. Okay. So this is basically the wave number of the hole. So hole is having a wave number of minus k. Okay. Now so how do you represent it? So you have one electron which is moved to the conduction band. So hole is having wave number which is minus ke, so which is given by this point. Okay. So this is the minus ke point, so it is formed at this point. Okay. This is one of the property. So now next property is about the energy. Energy will be energy of the holes will be equal and opposite to the energy of the electron. Okay. So this you can this also coming from the symmetry property. This you can actually prove the energy of the electron with the wave number Ke is equal to energy of the electron with the wave number minus Ke, because of the symmetry, inversion symmetry. And so you know the energy of the electron is equal and opposite to the energy of the holes. So we can write down minus epsilon h minus Ke. So this minus Ke is kh. Okay, is the wave number of the hole. And there is another important property, which is velocity of holes and velocity of the electrons are equal in magnitude, which is coming from the gradient expression. So this is basically the gradient actually gives you the gradient. So this is the momentum gradient in the momentum space. This is basically coming from the Vg expression. Vg is equal to h cross inverse, Vg equal to h cross inverse del k epsilon k. Okay. So this is the group velocity, and this is equal and opposite for the hole. Okay. Now you can see here the creation of a hole in the valence band and a hole in the conduction band. Okay. Or suppose you have an electron with Ke which is moved to conduction band. So it will be having it is leaving a hole here. Okay. Which will be having a wave number minus Ke. Okay. So this is like a reflected form. So a hole in this portion valence band with Ke is equivalent to an electron in the conduction band with the wave number kh. Now there is another important property which I will define in the next class. This comes about the effective mass of the particle. Okay. So we will discuss this concept in the next class, how to define the effective mass. So this is not the actual mass. You can, for a moment, you can assume this as the mass of the hole in the presence of the potential. Okay. Which is actually proportional to the second derivative of energy with respect to wave number k. Okay, d square epsilon by dk square. Okay, and here the effective mass can be even negative also. Okay, so the mass of the hole is equal to negative mass of the effective mass of the electron. Okay, this is one of the property of the holes. And accordingly, using the above properties, using the properties 1 to 4, we can actually write down the equation of motion for the holes also, and we know the equation of motion for the electrons in the presence of electric and magnetic field. So this equation is motion is written in the CGS system. Okay, in the left hand side you have the force, the various kind of force, which is given by H cross dk H by dt is equal to this is the Lorentz force, E is the charge of the hole, and E is the electric field, and 1 by c factor, this factor comes when you use the equation of motion in the CGS system. Okay, the velocity of the hole, and B is the magnetic field, and you know, kh is equal to minus ke, and for the electron, which is negative charge. Okay, and so you can write down the equation of motion for the electron as in this way. Okay, so now in the figure in the right hand side, you can have this the flow of electrons in an electric field. So electron will be flowing opposite to the direction of the electric field. Okay, so the current density, which is normally defined in terms of the flow of the positive charges, will be in the towards the right hand side. Okay, and for the holes, v velocity as well as the current density will be in the same direction, in the, that will be in the direction of the electric field. So these are the properties of the holes. Most of the properties are qualitatively, you know, from the semiconductor physics when you discuss the p type and n type semiconductor. Okay, so here we have discussed in terms of the wave number and the energy and energy of the holes. Okay, and the group velocity of the wave packet, which represents the motion of the electrons and the holes. Hope you understood the video. Thank you.